streaming thing here. But with that said, I want to start off by just sort of introducing myself, talking a bit about my background and how I came to be at IBM Quantum. Then I'm going to sort of dive into a presentation that talks about some of our quantum hardware. Should hopefully be spending about 15 minutes on that presentation. Then I'm hoping to sort of answer questions about that presentation afterwards. And then we can actually, after that, dive into the quantum coding and actually do some live coding. So with that said, as I told you, my name is Nathan Earnest-Noble. I joined IBM Quantum about a year ago. Before joining IBM Quantum, I did my PhD at the University of Chicago in experimental superconducting qubits. So I was explicitly focusing on how to engineer sort of next generation qubits and trying to make some improvements on the ones that we have today. It is still something that is in the early development stages, but it's something that I'm more than happy to talk about if you want. Before that, I did my undergrad at the University of California, Berkeley, where I was studying physics and applied mathematics, and then also focused on some Arabic while I was there. With that said, let me go ahead and just start off and take a look at the stream and see if there's any questions that you have, and I will answer them. I have another computer set up here, by the way. I'm doing a bachelor's in sorting algorithms. Awesome. Yeah, Potan cannot decide between being a particle and a wave, so it has to be in both. That's true. Until you measure it, I guess, and then it's going to be one or the other. Go Bears indeed, Animita. I miss Berkeley a lot. But how's everyone's day going? I know it's a strange time that we're in right now. I hope everyone's staying safe and staying sane, getting outside every so often when you can. Great question, Max. Hello, do you know when there is time-dependent frequency control during the pulse? So by time-dependent frequency control, I'm assuming that you mean you can actually adjust the frequency of the qubit during a single schedule. So in some ways, that's actually possible now, particularly on our Harmonic device with high resolution. But if that's not what you meant, let me know and I can follow up with that question. Yes, Encore, they are. How quantum computing is possible? I think quantum computing is definitely a very interesting technology that we're certainly working very hard to make it be as powerful as it possibly can be. There's some real challenges that the field has to overcome sort of holistically to make these a viable and useful thing for society more broadly. But what's interesting about these devices is I think they let you study some really interesting physics today and do things that you couldn't have done otherwise. All right, so with that said, let me go ahead and share my screen. Okay, so as I had said, my goal here is to sort of give this talk for about 15 minutes, at which point then we'll come back and answer some questions that you have. The focus of this talk will be sort of talking about the technology that we focus on at IBM. Sorry, my cat's making noise in the background. But we are, at IBM, we're focusing on superconducting qubits, and I'm going to get into some of the details on what that actually ends up looking like. So on this screen here, you see this thing on the right. People often call this the chandelier. So this is actually the inside of the dilution refrigerator that we have at IBM, which is the thing that we use to cool our devices down to the 15 millikelvin that they need to be at in order to operate appropriately. I kind of want to walk through this and show you different components of this and actually point out what's going on. So big thing is the quantum computer itself. So though these systems are very, very, very large, sort of in size, what you'll quickly learn is that the quantum computer, the actual quantum processor, is much smaller than the rest of the system and sort of exists inside this can right here at the very bottom. The exact size of it sort of will depend on what number of qubits you have on there. But the thing that actually ends up taking up a lot of the space in these systems is all of the control electronics that go along with it and all the filtering that you have to do to ensure that these qubit devices are sort of appropriately isolated from the environment to have the best quality that they can. Then here you can see these microwave lines. So these are the microwave lines that come up from room temperature all the way down to this 15 millikelvin temperature down at the bottom. And these are the things that actually allow you to port in the signals that will eventually control the qubits. One thing I just like to point out is you can see that there's this little loop in these lines. And this loop is actually important because as you cool these things down to such cold temperatures, you begin to get thermal contractions and things will slightly adjust in what size they are. And so you want to put these loops in here to ensure that your microwave lines don't break throughout the process. The dilution unit, so these are called dilution refrigerators, and the reason being is that they have this specific unit right here. And this is the thing that sort of does all of the cooling. So this is where the magic happens in terms of making these fridges as cold as they possibly can be. What's inside this dilution unit is sort of a mix between two different isotopes of helium. And there's some interesting physics there that actually allows this to end up being something that cools your system down to such cold temperatures. And then what you do is you sort of attach your quantum system to this bottom plate. And then there exist many different elements to ensure that this bottom plate is at that 15 millikelvin. Now let's go ahead and go to the next thing. So yeah, as I said, this plate here now is at the 15 millikelvin, which is sort of the necessary thing that we actually need to measure these devices. And I'll talk about some of that in a second as well. And then really what takes up a large chunk of the space are different microwave components and things that you put in there to sort of filter out various bits of noise or ensure that you have the optimal behavior of your quantum device. These right here are microwave circulators, which is a microwave element that sort of helps ensure that microwave light propagates in one direction, but not in the other, which is important when you're trying to control these devices carefully. Let's see. Taking a look out, I'm going to quickly click through all of this. So if you sort of take a step back, what this ends up looking like is this here, where you have, this is sort of the dilution unit without necessarily being completely set up. And you can see that there's the 15 millikelvin stage that I pointed at earlier, but it comes into sequentially higher temperatures as you go higher into the stage. And this is sort of important to actually ensure that you can get that device as cold as possible. Then the quantum processor itself is depicted here. This is an example of, I think, 7-qubit device. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So now this ends up being, so this chip right here is on the order of a few millimeters in size generally. And then it ends up getting put onto this board, which then gets connected to the bottom of the stage here. And then you can sort of hook up some JPCs. So these are Joseph and parametric converters. These are sort of our quantum limited amplifiers, the thing that sort of amplifies your signal as much as possible with adding the minimal amount of noise that you can. And then out at the top here, you sort of have all the classical control electronics that then get fed into this. And now what I think is particularly exciting about this component of Qiskit called OpenPulse is we sort of have opened up the avenue for you to begin to control these devices yourself, so that you can actually program at the level as if you were sort of an experimentalist in the lab. That being my background, this is something I'm personally very excited for because it really allows you to just be a quantum scientist to the fullest extent. I will quickly show you this, and then I'm going to just take a look for some questions. So what this process in the full looks like is you're going to have your classical computer here. And now you're always going to need a classical computer regardless of what stage we're at with quantum computing. And a large reason that is that you're going to use this classical computer to control the quantum computer. So what that ends up looking like is you're going to send in some instructions. They'll go down into the fridge and then do some measurements. So now here you say have QC measure. So this is the thing we're going to be focusing on today. What that does is sends in these microwave tones that have some amplitude and some duration. Then they go down through those filters that I was pointing at earlier. They interact with the quantum processor here, or the qubits or the resonators, whatever element it is that you're interested in. It comes back out, gets amplified through various chains, then sort of processes in some way, and you get these zeros and ones. And today I'm going to kind of help reveal how is it that we get these 0 and 1 measurements. What exactly is the thing that we're doing? What's going on? So now I'm just going to take a moment and try and look and see if there's some questions I can answer here. Hey, Yusuf, what's going to be demonstrated here? So today I'm going to be talking about how you actually do the measurement process for your qubits and how you can sort of calibrate that up. Kizkit, I think you need to add a course about quantum programming in Coursera. That's a good idea. Are quantum computers already fully operational? If not, how is it possible to do quantum computing? So this is a great question, Pierre. So in one sense, yes, quantum computers are fully operational. And today at IBM, we have quantum computers on the cloud that you can program right now. The challenge is those quantum computers are very noisy. And so what you need to overcome that noise is this thing called error correction. And that is the stage that we need to pass in order to actually get what's called a fully fault-tolerant quantum computer, which is the thing that will make our quantum computers do very powerful things such as Shor's algorithm. In between now and then, there's this sort of intermediate near-term compute or noisy quantum compute stage that we're at, where we're really trying to figure out how we can make those quantum computers as useful as possible today. Will the dilution fridge setup work if you scale the processor to a 3D architecture, which I suppose is a possible future path? So there's different ways to interpret 3D architecture here. Maybe I'll let you clarify what you meant by 3D architecture before I dive into that. Oh, hi, sorry, my cat again. So now let's go ahead and move on to the next slide for the moment. So I want to now talk about how we actually make the quantum processors. What is the specific technology that we at IBM are pursuing? So if you want to make a qubit, and if you've ever taken a physics class, you know that a physicist's favorite thing is the simple harmonic oscillator. So you might think that that's a nice place to start when trying to make a qubit. You can realize a simple harmonic oscillator in the electrical form through taking just LC resonate circuit here. So when you do this, and this here's the Hamiltonian, or using not jargon, this is the way to talk about the energy that is existing inside this circuit. Now you can treat this thing sort of classically, or you can treat it quantum mechanically. When you treat it in a quantum mechanical sense, what you end up getting is that it has discrete energies that are spaced out by h bar omega. So h bar is some constant, and omega is the frequency of transition. So this is, for our devices, around 5 gigahertz. Now this is a very enticing thing to try and use as your qubit, but you can't quite use it as a qubit simply because this h bar omega, if you wanted to use these two lowest energy states, say for your qubit states, your 0 and your 1, well, you drive on this h bar omega to try and take it from 0 to the 1 state. But then what you'd end up doing is driving on the 1, 2 and the 2, 3, and you wouldn't actually be able to get the coherent control between the two states that you actually want. Not all hope is lost. So you can make a superconducting qubit by adding this Josephson junction element. When you add this Josephson junction element, which is this element in the top right-hand corner, so what this is a non-linear inductive element. So here you had this linear inductor. What you're going to do is take that and replace it with this non-linear element here. So the Josephson junction is this tiny element here, and then these two large pads are the capacitors that make our qubit. So this circuit is known as the fixed frequency transmog qubit, and it's one such superconducting qubit that you can make. I'll get into some details in that in just a second. But by adding this slight nonlinearity here, what you end up doing is you take those energy spacings that previously were all equally spaced, and now you shift what the spacing actually is. By doing so, now you can actually coherently control the 0-1 transition. And so this now is able to be the qubit that we want it to be. I also just want to take a moment, this Josephson junction right here, this is very much so a workhorse of a lot of the technology that IBM Quantum is making. Namely, you can use this element to create qubits, but you can also use this Josephson junction element in slightly different ways to make those parametric amplifiers that I talked about earlier. And then there's just many interesting things that this Josephson junction can do. So it's a very, very useful device. Element in our quantum circuits, and it's very necessary. Now, how do you actually go and measure the state of these qubits? Well, what you're going to do is you're going to couple this qubit to this linear resonator right here. When you in this instance, we're doing a capacitive coupling. So we're taking some capacitor and we're putting it here. Visually, what you can see on this diagram here is that there's this slight little element that's red. Well, this is capacitance coupling to our readout resonator. These two here, say, are capacitive couplings to neighboring qubits, which I'll talk about in just a moment. When you build this architecture right here, where you have some linear element coupled in some fashion to your qubit, generally with a capacitive coupling, this is what is known as circuit quantum electrodynamics. So this is the circuit equivalent of cavity quantum electrodynamics, which is the thing that had won the Nobel Prize a few years back by David Wineland and Serge Haroche. But this is sort of the exact same physics, or much of the same physics, that you realize in a cavity, but instead of using nature's atoms, we're building these artificial atoms here. Now, as I had said, these devices are operated around 5 gigahertz. So this 5 gigahertz operation frequency corresponds to a temperature of around 240 millikelvin. And this is a very critical thing, because this really is what makes it necessary for us to cool our devices down to 15 millikelvin. Because otherwise, the thermal environment will excite our qubit and will make it very difficult to have any sort of quantum information inside. Now, I had mentioned earlier that you can't use this linear resonator as your qubit because you can't get the coherent control between your 0-1 states. Well, that actually doesn't rule this out as being a useful element nonetheless. Namely, you can use this element to do many different things. So specifically, it is the thing that allows you to do the readout of the qubit states. So I'm going to get into the details in just a second, but this basically comes down to the frequency of this resonator depends on the state of this qubit. And by that dependence, you can actually end up doing some quantum non-demolition measurements with this resonator here. At a high level, it just allows you to read the qubit out. The noise filter, so if you didn't put this resonator here, it would be your qubit would be directly exposed to the what's called the 50 ohm microwave environment. But basically, I was just saying it'd be exposed to all of the energy and all of the light that's propagating down through those microwave lines and wouldn't have anything to protect it from that. And so this linear resonator really does a good job at sort of isolating this qubit, but in a way that still allows you to control it. Now, you can also use this linear resonator to couple 2 different qubits together. And that's the way that it ends up looking at IBM. We take these linear resonators here, and we capacitively couple them to neighboring qubits, but then we use those same linear resonators to create a readout resonator that you can use to couple to the qubit to read out the state of the qubit. Now, the goal of today's coding component is that we're going to sort of get in and start tuning up the microwave tones that come in and hit this resonator at the frequency of our readout resonator, and actually begin to see how that behaves dependent on what the microwave light is doing. That said, let me take a moment and see if there's any specific questions that you have. Is the implementation on IBM Harmonic the same as the regular one? I mean, is the code work circuit.h, or is there a special one? Yeah, so IBM Harmonic is set up the same way as all of our other quantum computers. And so when you're programming IBM Harmonic, when you're doing the programming at the pulse level, you're sort of taking control and actually generating those waveforms specifically. But if instead you did the circ.hadamard gate on the qubit, you're just telling the backend, hey, you go and create that waveform for me, and I'll take the waveform that you very carefully calibrated, you being IBM in this sense. Wow. What are the advantages in quantum neural network over classical neural network? That's a great question, and one that I think the field is broadly trying to explore and answer. And I don't think that, I personally couldn't give you a simple answer, and I don't think that there is. Hello, how many microwave channels is used for each qubit? Great question. It really depends is the short answer. You end up having at the minimal sort of 2 channels generally, one to control the qubit, namely drive it and rotate the qubit state, and another to measure it. And when I'm using channel in this sense, I mean more in the programmatic channel sense, not necessarily the physical line going down. Awesome. Let's go ahead and continue then. One thing I want to say, so I talked about this circuit QED as the sort of paradigm that we're using it for. So we are using circuit QED as the way to build very good quantum computers. But you can use circuit QED for many different purposes. In the Nature of Physics channel, I actually recently published a lot of review articles on this field of circuit QED broadly, coming from some of the very initial measurements, actually being able to show that these macroscopic quantum circuits can behave quantum mechanically, to sort of the ever evolving field that is going on with it. So I think that a lot of these papers are very interesting, and I highly recommend checking this out if you sort of want to get a broad sense of what's going on in the field. So earlier I'd mentioned that we use the fixed frequency transmog qubit. So a fixed frequency transmog qubit basically consists of a single Josephson junction, as I had shown you earlier, shunted by a very large capacitor. You can instead have a flux tunable transmog qubit, where instead of just a single Josephson junction, you're going to put one right next to it and create a loop. This loop now is very sensitive to any sort of external magnetic field. So that can that I had shown you earlier that the quantum processor sits inside of is very important, because part of what it does is helps filter out any external magnetic fields. So at IBM, we're deciding to stick with these fixed frequency transmog qubits. Part of the reason to that is that they end up being the best quality qubits that you can have. Namely, when you put this element in here, it becomes very sensitive to any external magnetic field. So from some previous experience, if you don't put it inside that can and you have this flux tunable element, it is so sensitive to any sort of external magnetic field that if you walked by and took your phone and waved it around the fridge, you would see your qubit frequency shaking about. So this is in part the reason that we're trying to stick with these fixed frequency elements. So one of the advantages is that they remain sort of with a high coherence. So they aren't susceptible to flux noise in the same way that these tunable elements are. Another thing that's actually nice about this is that instability that comes from this flux tunability that you have in this flux tunable transmon is that by getting rid of that flux tunable element and just making it fixed frequency, your gates will remain far more stable. So you actually have to very carefully calibrate the gates that you use to control these qubits. And if you have this tunable element, it's possible that the frequency of your qubit shifts slightly. And when your qubit frequency shifts slightly, then how you actually control it has to be updated with that shift. And by getting rid of this tunable element, you can have calibrations that are stable for hours to days. And that's a very nice thing. Some of the disadvantages, so this does sort of restrict what sort of gates you can necessarily do. By having this flux tunable element, you can realize different sorts of gates that you can't necessarily realize in the fixed frequency element. And this really leads to all microwave controls. But I think that there's a good argument to say that by keeping this fixed frequency component, you can sort of get the better coherence that you want your qubit to have, and thereby be able to sort of get a higher quality quantum computer that you can scale up. I want to briefly say this is just two examples of superconducting qubits, or two examples of artificial atoms that exist out there. And there are many different sorts of elements. So instead of having your Josephson junction shunted by a capacitor, you could have it shunted by an inductance. And then that leads to this sort of qubit called the flux qubit. And then you can actually create very sophisticated different sorts of qubits that might be interesting avenues moving forward for this technology. However, to date, the absolute best qubit that exists in the superconducting platform are these fixed frequency transmog qubits. So now this is where I'm going to get into how the measurement process actually works. So to start, you take some tone of light, some microwave tone, and you're going to drive your qubit. And I'm going to leave this detail for next week, where Lauren will hopefully be talking about how you can tune up these gates that sort of rotate your qubit states. But for now, just imagine this is some tone that does something to your qubit, and then you're going to follow that tone up with another tone that is at the frequency of your readout resonator. By doing this, then you end up sort of reading out what the frequency of this resonator is, and then thereby what the state of your qubit is. And I'll get into how that works in just a moment. Before having OpenPulse, whenever you would do measurements on our systems, you'd get what is sort of being called measurement level 2. So this is where you would measure, and then you'd sort of leave all the magic behind the scenes and let IBM sort of tell you, hey, is it a 0 or is it a 1? And you wouldn't worry too much about how they got that answer of whether it's 0 or 1. But today, now with OpenPulse, you can do this thing called measurement level 1. So this now is where you can actually read out the microwave tone that is used to determine whether you have the 0 state or the 1 state in your qubit. Specifically, what's being shown here is the I and the Q quadrature of your microwave tone. So this is sort of the real and imaginary components of this microwave signal that you're sending down into your fridge. And then what you see on the plot itself is a collection of blue dots and a collection of red dots. So the blue dots are when the qubit's in the 0 state, the ground state, and the red dots are when the qubit are in the 1 state. And how you actually get it from the 0 state to the 1 state is not something I'm going to worry too much about today, but I'm just going to sort of say, hey, we have some ability to take our qubit from 0 and put it into 1, and now let's start to think about how we can calibrate our readout of those two different states. When you have this IQ plot here, you can then use it to create a linear discriminant analysis, say, is one example. But broadly, you can come up with different ways to have a computer tell you this dot appeared in this part of my IQ plane, so thereby I know that the qubit was in the 1 state. Whereas a separate time, I measure the qubit being over here, and you could see that the qubit is in the 0 state as a consequence. One thing you might know if you're looking carefully is that you can see some blue dots are in the area where the red dots are, and then some red dots are similarly in the area where the rest of the blue dots are. And this can be due to different reasons. And largely that just gets lumped into this thing called spam errors, which is state preparation and measurement errors. And there's a lot of different ways that those measurement errors can come about, or state preparation and measurement errors can come about. Nonetheless, you can use this to now create your own discriminator. So whereas before you would sort of get these 0-1 measurement readouts, now you can actually go get the IQ quadratures of your microwave tone, and then from this construct whether you have a 0 or a 1. And we're going to sort of get into some of the details on that in just a moment. Something else that will eventually be available is this thing called measurement level 0. So in this measurement level 1, each dot here is actually the average of some data that is taken throughout time. Now, this measurement level 0 can actually allow you to track the time dynamics of that measurement tone. And there's some interesting physics that you can do to, say, improve the state of your readout. Or maybe even more broadly, you can begin to apply machine learning techniques to this sort of raw data here to actually be able to try and get improvements in your readout fidelity. Now, I'm going to take a pause here and just see if there's any good questions or any questions broadly. I'm a computer science major. Should I major in mathematics or physics too? I think major in the things that excite you and study hard. I think what's exciting about this field of quantum computing is that there's many different ways that you can come into it. You can come as a mathematician, you can come as a physicist, you can come as a computer scientist. It is a very diverse field, and just being able to learn as much as you can, I think, is really the suggestion. I think computer scientists can really, at this stage now, especially, start doing some really exciting work in the field of quantum computing. I think adding physics or math are both beneficial to that education. Do you apply any algorithm for optimal control of pulses? That's a great question. That is absolutely a field of research in which now you can actually begin to think about how you shape these pulses very carefully to achieve some improvement in your calibration. There are some papers that IBM puts out with relation to this. I today won't be talking about that. Why is the computational basis the only basis where we can do a measurement? So if I understand you correctly, you're saying, why is it that we can only measure in the 0 and the 1? In actuality, taking a moment to go back here, as I had said, these devices have many different energy levels associated with them. And so though we use these transmon devices as qubits, they are more generally actually qubits. They have many quantum digits, so to speak. So there are other energy states that exist here. And when you do so, speaking specifically, say, to this higher energy 2 state, you can use your measurement process to read that out as well. And that would end up being a separate blob in this IQ plane. So your measurement process is not just limited to the computational basis, if I've understood your question correctly. Awesome. Let's see, what else is there? What's the difference between the flux qubit and the transmog qubit? So the transmog qubit is what's shown here, where you have a single Josephson junction shunted by a large capacitor. And it doesn't necessarily have to be a single Josephson junction, actually. It can be two of them, which is the thick tunable transmon element. The difference now between a transmon or a flux qubit is that instead of this large capacitor, you would shunt it with an inductive element, and that now would be the flux qubit. And it's called as such because of the flux that sort of goes through the inductive element there. Yeah. What I want to say is that the transmon has many different names that people will call it by. So there's the Xmon, the Gmon, the Ymon. A lot of people have come up with different things that tend to reflect details about the physical architecture of the qubit, but the qubit is in many instances the same sort of underlying qubit. Namely, it still has this single Josephson junction with a large shunting capacitor here. And this transmon element, by the way, is sort of the third generation of charge qubits, so to speak, where a lot of people have thought very carefully about how to make this sort of charge-based qubit as robust to noise as possible. When I say charge-based qubit, it's now because we're thinking about the charges on this capacitor here. Great questions, everyone. Thank you. Let's see. How often are qubits calibrated? That's a great question, Max. So I think that it really ends up being calibrated as much as necessary in some sense. So there was at some point when I talked about the benefit to these fixed frequency elements or these fixed frequency transmons is that the calibration remains fairly stable for hours to days. And when I say fairly stable, I'm really talking about very, very small shifts in these things, which become quite important because you want to get the best gate that you possibly can. But it can say now come down to a shift in your frequency from these things being up at gigahertz. You can have shifts in your frequency on the order of kilohertz, say, that will affect your qubit. And I'm not exactly sure about those precise numbers, but it is something that you end up doing. You want to do calibrations for as much as you possibly can to get the best gates that you can. On average, I would say think about it being done once a day. How flexible is this platform to be used as qubits? Great question. They are naturally sort of quantum digits, so you could use these transmon elements as qubits. There's a paper out from Irfan Siddiqui's group at Berkeley where they actually use this two-state to start thinking about information scrambling and sort of modeling black holes through these systems, which I think is exciting. So it can be done now. There's some constraints that you have to think about and how to do that well and what's the best way to couple two qubits together. But yeah. Are there internships this summer? Yes, there are definitely internships. Go check out IBM Quantum Internships. I'm sure if you look it up, you'll be able to find it. I don't have the exact link off the top of my head. Great. All right, so let's go ahead and move forward a little bit. So I talked about these three different measurement levels that you have with OpenPulse. One thing I want to say is that this measurement tone here or how these measurement results turn out depends on many things, some of which is the amplitude. So how bright is this light that you're sending down into your fridge? the frequency of this light, so what is sort of the color of the light that you're sending down, so to speak, and how long you're going to be reading these, sending these tones of light down into your fridge. And in the next slide, I'm sort of going to talk about specifically that last element of how you can adjust the duration of these pulses and how that ends up affecting the measurement readout that you get. So how does this measurement actually work? Here is just another way of looking at that same transmon device that we had earlier. So here at the bottom, you have some transmon element that is capacitively coupled to the center transmission line right here. There's two breaks in the center transmission line, which then turns this into a linear resonator. And then on the outsides here, this is sort of the ground plane that you to actually create the quantum circuit that you're interested in. Down here, you have this Hamiltonian. And what this Hamiltonian is doing is it's modeling your qubit as a two-state system. So we're going to ignore for now that there's these higher energy levels and only think about it as being a two-level system. And then this A dagger A is sort of the number operator. So this is telling you how many photons do you have inside your linear resonator. And now what you can see from this is that the state of your qubit, so if you're in the 0 state or the 1 state, will shift what the corresponding resonant frequency looks like for your readout resonator. Now, that's sort of what's shown here, whereas your qubit, if it's in the 0 state, your linear resonator, that's right here, will have some frequency omega minus chi. And then if it's in the 1 state, it'll have some other frequency omega naught plus chi. This chi right here is sort of the shift of your readout resonator. And this is something that's very important that you sort of want to tune up to get the best possible readout that you can. If we end up having time, I have a notebook that sort of shows how you can do this. One thing I want to point out is that you have this center peak here as well. This center peak corresponds to the what's called the bare resonant frequency of this linear resonator here. So what that is this is the frequency of your resonator if you didn't bother coupling your qubit. And then the width of this resonator right here tells you the quality factor of your resonator. And you tend to want to make this resonator very broad because what that helps you do is it allows the photons to quickly leak outside of this resonator and into your amplification chain, which then allows you to do fast readout. And generally, you want to do your readout as fast as you can, but with the best quality that you can, so you can begin to think about how to do conditional operations on it. And then, yeah, as I had said, if you have your qubit in the 0 state, the peak would sort of be at this frequency. And if it was in the 1 state, it would end up being in this frequency. And now with this, you can already begin to see how adjusting the frequency of your readout tone will impact the quality of the readout. Namely, let me just point out, if you ended up reading at this omega naught frequency right here in the center, and this was the frequency that you probed at, what you'd quickly realize is that you would be incapable of discriminating whether your qubit's in the 0 state or if it's in the 1 state, because you wouldn't actually see any shift in sort of how much this peak goes up or down when it shifts from being in this state to being in this state over here. However, if I went and put my frequency here at the top of where my 0 state is, what I'd get is I'd read out a signal right around at this amplitude if it was in the 0 state, but I'd end up reading it out around this amplitude if it was in the 1 state. And this is one way in which caring about the frequency can affect the quality of your readout. Now, today, what we're going to do is we're going to keep that frequency fixed, and instead, we're going to look at the other two components, sort of how long is that readout tone going, and then also how large is that microwave. So first, looking at the duration of the tone. So here is the sort of OpenPulse schedule that we have. We're going to have two different versions of this. One that has this D0 drive, so you actually take your qubit from the 0 state and then pulse it into the 1 state. And then we're going to have another schedule where it doesn't actually exist and there's no pulse and you only do the measure. So if you kept this amplitude fixed and look at this duration right here, this is sort of the IQ blobs that you end up getting. Now what you can see is your 0 and 1 blobs are not very well separated, so they're almost overlapping entirely. And in the code, we'll sort of go through this and show you how you can see this for yourself. But you quickly realize that if you tried to do readout with this quality of readout here, it wouldn't work very well. You'd get a lot of incorrect classifications of when you knew your qubit was actually in the 1 state, but it gets classified as being in the 0. So one thing you can do is now take that duration, that pulse, keep the amplitude fixed, and increase the duration. When you do so, now all of a sudden you can see that the 0 blob and the 1 blob become well separated. So now you can actually go and create that discriminator that allows you to say, if your dots are appearing over here, you're in the 0 state, and if your dots are appearing over here, you're in the 1 state. Now you might think, okay, so I've taken that pulse, I've increased its duration, and it's improved. So now I'm just going to take that pulse, increase the duration for even longer, and get an even better readout. Unfortunately, that doesn't work too well, because if your readout tone starts to become an appreciable fraction of the T1 of your device, the T1 is how long the qubit sort of stays in the excited state before it decays back down to the ground state, or it's a way to characterize that. So if your readout time becomes an appreciable fraction of that T1, what you'll actually start to see is your qubit decay during the readout process. So this sort of goes to say that you can't win by just taking that pulse and making it indefinitely long. There's sort of an upper limit to it, and this is one way in which you can begin to think about sort of calibrating that pulse. So this is I think the end of the slides that I've put together. Now I'm going to take a moment to sort of jump into the code itself. Before doing so, I'm just going to look at the channel, see if there's any other questions I can answer. I see someone's writing in a language that is not English. Sorry, I cannot help. Is it possible to apply multi-qubit gates directly? Yes, so you can definitely apply multi-qubit gates, and you can do that at the pulse level. Publicly, we have our Harmonic device, which is a single qubit device, so you can't explore multi-qubit gates quite yet, at least at the pulse level. There does exist other multi-qubit devices where you can take these gates and apply them, but you can't adjust the waveforms yourself. All resonators have the same omega R roughly? So that's a great question. You can't have the readout resonators or any resonator, frankly, have the exact same frequency, because if it has the exact same frequency, then it's difficult to excite only one of those elements. And that actually becomes a large challenge when trying to scale these devices up well, because the fabrication is a non-trivial thing to do to get correct. Hi, greetings for Denmark. Hello, welcome. All right. I think that's great. I've answered the questions that I think I can now. So let's go ahead and jump into the coding component. So this is, so can I just get a confirmation that we can see the slide, the screen? Awesome. So here, I'm just going to start off by going into quantum.computing. So this is our IBM Quantum Experience sort of platform. So this is where you can come to learn about quantum computing and even execute some notebooks. What I want to quickly point out here on the right, we have some notebooks where you can access Jupyter notebooks that give you sort of various tutorials on how to operate these devices. I'm now going to focus on the notebooks that I've uploaded. Namely, I'm going to start with this quantum coding with Qiskit, and then maybe if we can, we'll get to this second notebook. So going to that. So this here is our quantum coding notebook. And again, the goal here is that I want to sort of show you all how you can take that amplitude and adjust the amplitude and then see how the blobs will correspondingly change. So to do this, I'm going to import some elements. A very critical part of the element is this pulse component. So this is the part of Qiskit that actually allows you to begin to program at this pulse level. Another important thing is this pulse lib. So this is where the various different waveforms will sort of be defined. So you can have a Gaussian waveform, a square waveform, or really at the end of the day, you can make an arbitrarily shaped waveform that whatever it is that you're interested in. Then I'm going to just quickly point out there exists sort of the drive channel, measure channel, and acquire channel. Today, we're really going to be thinking about these measure and acquire channels because these are the things that actually uh, uh, are what we're going to be studying to try and tune up how do you actually get this measurement pulse to be as good as possible. Next week, we'll be talking more about some of this drive channel stuff. So I have my account loaded here. I'm going to be using just a specific device called IBM Almaden. If you wanted, you'd be able to change this to IBM Harmonic, and everything should be able to behave as well. You might need to take into consideration that some things will change. Namely, one thing that will change is the DT. So this right here is the resolution of the backend that you have. So for Almaden, we have a 3.5 nanosecond. That should say nanoseconds. But for IBM RMonk, if I just go ahead and come in here, change this to RMonk, what you'll see is that resolution is 2.22 or 0.2 nanoseconds, actually. And so this will end up changing some of the details. Namely, you'll have to adjust your measurement time, which we'll see in just a second. Just to make sure everything works well, I'm going to keep it with RMonk. So this is the back end here. So this is just showing you what the back end looks like. This is, I believe, a 20 qubit device with a quantum volume of 8. This is something that we measure and update daily. And then you can see 0 pending jobs, but really getting down to some of the interesting stuff. So here you can extract what the qubit frequency is. So you can see it's around 4.85 gigahertz. This right here, because I'm now doing that measurement level 1 as I talked about, this is just the way to take those signals and extract the amplitude of these I and Q quadratures. The calibration, so this right here is something that is going to be very useful for us to sort of gleam over this one specific gate that's important. Namely, it's this X gate. So the X gate is the gate that takes your qubit and pulses it from being in the 0 state to being in the 1 state. We define it with this U3 operation and the appropriate angles for that. And so this is something that you can go ahead and code up yourself, so you can actually define this X gate from the ground up, so to speak. For the sake of staying focused on the measurement, I'm going to just take this from the back-end calibration so that we don't have to worry about it. As a starting point, you can also do the same thing for the measure pulse. And so I just want to end up showing what that looks like. So now we're going to go ahead and define these measure, drive, and acquire channels. And then now I'm going to do, for the sake of convenience, define a measurement time. So this here is in DT. So this is going to be 50 DT, which then corresponds to roughly 150 nanoseconds after you, from the start of your circuit. So we're going to create our first schedule. And the goal here is to sort of compare those two 0-1 distributions that we saw earlier. I'm going to then go and add my X gate that I've defined up here. And then I'm going to go ahead and just take the default measurement gate and add that as well. And I'm specifically adding that at the measurement time that I've defined right here of 50 DT. So now if I go ahead and draw this, you end up getting this plot right here, where what you can see is this is your X gate. So this is the concatenation of 2 pi/2 pulses, they're called, that leads to the X gate that you want to have. And then on the right here, you can see the measurement tone and then the subsequent acquire tone. What I want to point out is the measurement tone refers to photons being sent down into the readout resonator, where this acquire tone is telling you that you actually want to take whatever signal is coming out from your readout resonator and acquire it. This might seem obvious that you would always want to do this, but there's actually ways where you can decouple these two and then only have this measurement tone, which allows you to do some interesting physics that maybe I'll have the chance to talk about. Namely, you can start to count the number of photons inside your resonator. We're putting together a notebook to show that, which is exciting, I think. Then I'm going to create another schedule as well. This schedule is I'm just going to call it measure schedule. And the goal here is that instead of having this pulse where I pulse the qubit into the one state, I'm just going to directly measure the state of the qubit at the start. And this now will allow us to go ahead and compare our 0 and 1 blobs. So I could go ahead and run that. Just because sometimes there's a queue in which I have to wait for these things, I went ahead and ran it before. So I'm going to take one of these examples. And then now you can see that you have your 0 blob here and your 1 blob here. So the 0 being the gray dots and the 1 blob being the blue dots. And again, you can see that you have some spam errors where your qubits, where the 1 dots are appearing in the 0 blob area. So now that's awesome. We can now go ahead and say construct a very simple discriminator. This discriminator is just going to say, I'm going to take the mean value of these blobs, and I'm going to call this sort of center part of that. So the mean value of that, the ideal 1 value. I'm going to do the same thing for the 0 over here and call the center the ideal 0 value. And then I'm going to say whichever blob center is closer is going to be the one that I will define as being, or is how I'll classify. So this dot right here is closer to this center, so I'll go ahead and identify this as being the 0 state. Now you can see that this isn't true in what I've plotted here, but that's simply because I know that these blue dots should have been the 1 state because I did the necessary code up here to do so. But if I didn't know that, which is the case when you actually run these quantum circuits, then you need to create a discriminator, which is then what I've just said. And then now you can see that about 86% of the time, the qubit ends up in the excited state here. And then this 86% number is from just the spam errors that I talked about. You can what you can do to fix this is apply readout error mitigation, which there's a different notebook to talk about that, and sort of improve the results through post-processing. Okay, but now I actually want to go and calibrate this thing up myself. So rather than taking that default pulse that I have here, rather than taking this calibrated get measure pulse, I'm going to go ahead and tune it up myself. When I tune it up, I have different things. So this here, because in some instances you have a higher resolution backend, you just need to ensure that things come in multiples of 16. This here is just helping ensure that you're telling the backend how to appropriately measure the correct qubit, and that this is just helping address what the different resonators and whatnot are for the qubits, and I want to measure my qubit 0, say. This here, measurement with amp, is now where I'm going to go and begin. So before in the plots that I was showing you, I adjusted the amplitude. Well, instead, or sorry, in these plots here, I was adjusting the time. Now, instead of adjusting this time, I'm going to take this amplitude and slowly increase it. So again, keep those measurement samples fixed. So the measure samples here is the duration. This sigma and rise fall sort of tell you how this waveform at the end is going to rise or fall, at the edges more so. And then now I'm going to go ahead and use that pulse library that I mentioned earlier. I'm going to pull out a Gaussian square pulse. And then here, I'm going to take those measure samples, which will roughly be around 4 microseconds. And then the big thing that I'm going to be changing here is the corresponding amplitude that we put inside. So then now I have my measure schedule. As I had said earlier, we're going to go ahead and attach an acquire to that, just so that we actually download the information. And then we're going to go ahead and spit that out. So then now this is what we've done here, where I say have made 2 different schedules again. So one, I've done a measure schedule where I'm not actually exciting the qubit state, but I'm using that measurement pulse that I've constructed just here with the given amplitude of 0.05. This is sort of in arbitrary units. It goes from a value of 0 to 1 being your max. Then I'm going to do another schedule where I take my qubit and excite it to the 1 state, and then I'm going to do the measurement again. And again, I'm putting this at the measure time. So we're going to go ahead and create that. And then now if we wanted to look at what that looks like, we see, so this here is the excited measure schedule. So I've excited my qubit and then I'm measuring it and also acquiring that measurement. You can see that the amplitude here isn't very large. But if instead I came by and adjusted this to, let's just put it at 0.99, go to the max, you can see that that value, this amplitude here has gotten much larger. So now what I've done beforehand is I've scheduled different measurement amplitudes, and I want to show you the corresponding results. So I ideally could go in, submit another job where I have my measure schedule and my excited schedule. I'm going to return sort of single values because I want to see those individual dots. I don't want to just see the average of them. And I'm going to, again, do this measurement level 2. So if I switch this to measurement level, or sorry, I'm going to be doing measurement level 1, but if I switched it to measurement level 2, this is the thing that would actually just give you the 0, 1 value of your qubit. So now I've gone ahead and run some examples. So let's go ahead and start off at my index of -2. So I'm going to look at what does the signal look like when I have a measurement amplitude of 0.2. When I do that and it loads, you can see, hey, look, we have our two different blobs, the 0 blob with the gray dots and the 1 blob with the blue dots. Great. There's some different activity going on here, which might be interesting or something we could explore. But then now instead, let's go ahead and look at the first value. So now I'm doing a very small amplitude of 0.01. When I do that, you can see now, oh God, the 0 blob and the 1 blob are right on top of each other. And so now you can't actually discriminate the 0 or the 1 anymore. Okay, well, I've just used too small of an amplitude. Let's increase it a little bit. I get a, oh, it's all right. Maybe it's a little better. I'm beginning to see those blobs separate. This is a value of 0.03. Now let's go to let's go a little higher. All right, so now we're at a 0.05, getting better, still not great. Those two blobs are still overlapped quite a bit. Go one value higher. 0.1, all right. Hey, look, the two blobs aren't so bad now. You can see a nice, decent separation between them, but maybe I can increase a little further. Go to 4. And then now you can see that you've had these two blobs that are well separated. And then now if you, I didn't go too crazy with this, but I think if you increase the amplitudes a lot, you can begin to see some interesting nonlinear effects, which is sort of what is going on over here, I think. Yeah, I think that this is the conclusion of my talk. We are around 2 minutes before. I want to first look at some questions, and then maybe I can talk a little more after that. So let's see. Thank you. I need to learn more before coming here. Well, awesome. I hope you still had a good time learning this, and definitely keep coming back. We're going to have more of these to teach. And also, please feel free to provide some input as to what you think would be great to learn. What are the types of measurements that can be done? So you can really adjust those microwave tones in a lot of different ways, and you can do a lot of different interesting physics with that. Great. I see that there are some IBMers on here. Hi, Robert. Good to have you. The measurement pulse command is a Ramsey sequence like. So the Ramsey sequence that you're talking about is actually how you deal with controlling the qubit. So that's not something that we discussed today, yeah. And sorry, let me go ahead and stop sharing my screen so you can see me. But so that Ramsey sequence that you bring up is an example of one of the measurements you do when trying to sort of finely calibrate the frequency of your qubit. And it's also a good way to measure the T2 of your device. So it's separate from this measurement stuff that we've done today. Do you have any insights as to why operations sometimes fail? That is a fantastic question, and one that unfortunately doesn't have an easy answer. Operations can fail for a lot of different reasons. Some say when we're looking at the plot that I had just had up a moment ago, where you have the blue dots that are supposed to be the 1, but in the area where the 1 is, that sort of error can happen because of that decay process that I mentioned, the qubits decaying during your readout process. all this stuff is probabilistic. So even if your thing's very short, there is some sense of probability that it will happen. Another thing could be that the qubit was not exactly at that 15 millikelvin that you wanted it to be at. And so consequently was in the excited state, the thermal environment still sort of heated it up. And then from that, you would end up getting similar errors because you meant to pulse it from the 0 to the 1, but instead you pulsed it from the 1 to the 0. There's a whole range of things that can actually lead to different sorts of errors. And today I've only talked about the measurement errors, let alone the gate errors that you would have from controlling the qubit. So there's a lot of different things, which makes this both a very challenging field, but a very exciting one, I think. How do you create superposition in the superconducting qubits? Great question. So please come back next week. That's where we're going to be talking a little bit more about the control of the qubit, where you do what's called a Rabi oscillation, where you can actually go and create that superposition of 0 and 1 states. So we're at the hour now. So I'll go ahead and take a few more questions. I also welcome just broadly any questions, but I think we're about to wrap up soon. I see a question here. What do you mean by Gaussian pulse? So the Gaussian pulse is the shape of that waveform. So you saw one shape that was sort of square, then a Gaussian is just sort of a Gaussian shape. A Gaussian is a function, and then you can look that function up and it sort of looks like the waveform that you saw there.
Hey, Nate, great job.
Awesome.
Do you want to maybe find one more final question and I can let people know when they can tune in next week?
Yeah, sounds great. I'll find one more question real quick.
Okay. Hey everyone, thank you again for watching. We really appreciate this. We're adjusting and figuring out what works best for everybody. So all feedback is great. Right now we're planning on doing these every Wednesday. And so we're figuring out the best time or changing them so that people around the world can tune in. And we are archiving all of these on demand, so you can watch those as well if you want to subscribe to the channel.
Awesome. I think I've answered a lot of the questions.
Okay.
So I'll go ahead and end it there, I think.
Okay, Nate, thank you again. Where can people go to maybe reach out to you or follow up if they have more questions?
Yeah, fantastic. Definitely feel free to reach out to me through LinkedIn, and I will be responsive there. Always add a little note saying that you heard me here and I'm more likely to respond. Or more broadly, reach me on Twitter. I think they tagged my Earnest channel stuff, so you can reach me there as well.
Great. Yeah, we also have a Slack channel for Qiskit as a whole, and within there we have a channel called Qiskit-Live, and I'm sure Nate can keep an eye on that as well.
Yeah, and you can find me on there. I'm Nate Earnest-Noble or Nathan Earnest-Noble, and you can Slack me messages there anytime.
All right. Thanks, Nate.
Bye, everyone.